People have kind of contact with mathematics when they're in school, and so if you say
Mhm.
that you like do math, and they're like, "Oh yeah, I add numbers together too. I know what's going on there." When you say that you're in physics, though, that's already a huge barrier. And then when you say that you're in quantum information or quantum computing, that's already you've pretty much lost everybody by the time you get there.
Welcome to Impact Quantum.
Quantum podcast, turn it up fast. Candace and Frank blowing my mind at last. Quantum podcast, they're breaking the mold. Science and sky beats, it's bold and it's...
Hello and welcome back to Impact Quantum, the podcast where we explore the emerging field of quantum computing and what that means for the job market at large. You know, you don't need to have a PhD, don't need to be a researcher, you just need to be a little bit curious. And with me is the most quantum curious person I know, Candace Kahuli. How's it going, Candace?
It's great. I want to say Happy New Year to you because you still get to say it, I think.
That's
It's
right.
just,
We're still in the first week of January, right?
you still get to say it. Exactly. So I'm really excited because today we have Thomas Baker, and he is Canada Research Chair in Quantum Computing for Modeling of Molecules and Materials from the University of Victoria. So
Well,
how
yeah,
are you, Thomas?
I'm doing well. Happy New Year to you guys too, and
Yeah,
thank you for having
thank
me
you.
on. I'm glad to be here.
Thank
Awesome.
you.
So that is quite a mouthful. So
It's a tongue
what do you,
twister.
well, yeah, like, when presumably you were at cocktail parties or holiday parties, like, what do you tell people you do?
First of all, I try and allay their fears. I think a lot of people have kind of contact with mathematics when they're in school, and so if you say
Mhm.
that you like do math, and they're like, "Oh yeah, I add numbers together too. I know what's going on there." When you say that you're in physics, though, that's already a huge barrier. And then when you say that you're in quantum information or quantum computing, that's already you've pretty much lost everybody by the time you get there. Um, Really, what I do is I'm trying to figure out how to use and how to make quantum computers, which is a fundamentally new type of computer. So everybody watching this is probably using some sort of computer, either in their cell phone or in their laptop. And quantum computers are able to do computations with fundamental laws of physics. And the idea or the hope is that we can derive different results that are more efficient than what you can get with classical computers.
Oh, I like that. That was really straightforward. Was really fantastic. I wish you would have been with me when my son was here over Christmas and I could have given that answer. And I'm talking about the infinite possibilities between 0 and 1. And I'm like, no, 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 I've totally lost him. I've totally lost him, spooky and distant since he's done. But that was really, really interesting. So
Sure.
let me ask you this, okay? So what first drew you to quantum computing? Was there a
Oh,
specific moment, a problem, a curiosity?
yeah, great question. So I was floating around in another field of physics, condensed matter, before jumping into quantum computing, and with a little bit of quantum chemistry. It turns out that everything that I was working on falls under to what I do now. So right now, my position is this big synthesis of everything I've done in my life. Um, but the point that I really got into quantum computing was actually through one guy at the University of Sherbrooke, where I did a postdoctoral position for 3 years. And his name was David Poulon. Unfortunately, he passed away right at the beginning of the pandemic. But before that, even before I'd met him, he put out this paper basically saying that the current way that we were thinking to generate the initial state on the quantum computer was not all that efficient. And this had just it had ricocheted through the community. So I actually heard someone talk to me about this paper, and then they said, okay, quantum computers might not be that good. And then when I went there and I realized that it was him and that they were offering me this incredible position to go work with these incredible people, I had to say yes. And so I wound up going, and I remember he kidnapped me into his office in the first day that I was there and held me for 3 hours while he explained everything that he knew about quantum computing. And I picked up maybe just a little bit of it, but it was enough to get me thinking like, okay, let's try and do this. And then he threw a really hard problem at me. that we kind of solved there at the end. But it was just a good training experience. I found that it was testing everything that I'd ever done before. I didn't have to leave anything behind. And I just thought, this is the thing that I need to dive into and figure out.
Very cool. Very cool. What's exciting, I read your bio, which is both in English and French, or at least your hello, bonjour. So Candace actually lives in Montreal. My dad's side of the family is from Montreal. So I appreciate the francophone outreach. So you're researching about how to use quantum information to find new ways to work with chemistry, computer science, and physics. That's interesting, because most people we talk to tend to isolate in like one of those silos. You're really the first person I've seen that does, I wouldn't say you're a silo smasher, maybe you are, I don't know, but like you kind of work across those three different verticals. I think that's interesting.
Yeah, it's hard though. I've met a couple of other people that have been kind of shoehorned into this interdisciplinary thing. And you probably see a lot more people that are in one silo, or however you want to call it, just because it's easier. If you get to know a group of people, then you can send your papers out to them, and there's some general familiarity with the work that you've done before. I have to, hats off to the people in my group. Oftentimes we're writing papers in between several different fields. And if you get the referee that has been working in one of them and you approached it in a different way, then this can be really a calamity that is waiting to happen. I would say that the point where quantum information and quantum computing is at this point, you need the people who are interdisciplinary. You need to be thinking in different ways. A lot of the proof of principles come from really heroic papers coming out of what I would say is largely computer science. So computer science, like modern computer science, is like, here's like software engineering, and here's how we make the cache size different on a computer. But like old school theoretical computer science, where they're like analyzing stability of algorithms or updating matrix operations on a computer, some really brave people decided to try and figure out how quantum computers could work. And so a lot of our first demonstrations of how quantum computers could work are more computer science. But that original dream of, we want to actually model quantum systems, we actually want to do things in quantum chemistry, we want to go beyond what we can do with our best supercomputers on the quantum computer. These are all things that require the interdisciplinary knowledge. And so what you've seen a lot of teams of people. So a lot of like huge author lines where they get somebody to try and go between all those little subgroups in the team. I think one of the advantages in our group is that we're throwing everything against the wall, seeing what sticks, and trying to publish what we can.
Interesting.
So by working on all these papers, you must come across really exciting breakthroughs in quantum algorithms and error correction. Is there anything that really stands out?
Yeah, I mean, well, so the recent stuff, there's been like a subtle algorithm revolution, I would say, that's been going on, both classically and in quantum computing, because people who have worked on sort of one area, like maybe a tensor network, whenever there's a quantum algorithm that comes out, it better be tested against the top of the line, the state of the art, to see if the quantum computer can actually beat what's on the classical computer, because we're talking about an investment of millions of dollars. So you better test it quite rigorously and see what can happen. The point where quantum computing is right now, though, is people are starting to use actual properties of quantum physics, including things that aren't necessarily proven mathematically. We just, in the physics training, you kind of do what works, and you're supposed to move fast and break things a little bit. You're supposed to be careful and do the right things. But if you're using some 30-year-old hypothesis to base your quantum algorithms on that isn't necessarily proven, I can see how people in other fields wouldn't necessarily stumble onto that. So I think what's really been exciting recently has been, how do we actually use even untested things in quantum mechanics in order to actually try and find solutions that might actually work for what's going on.
That's interesting. You have to go through and kind of prove that stuff out.
I mean,
That's interesting.
if you start from a contradiction, you can wind up with anything, right? So, like, there's that old argument from Bertrand Russell, the logician, and let's see if I get it right. It's like if you're standing next to the Pope in a room, you start from a contradiction that just like 1 equals 2, then someone might reasonably come up with an argument to say that you're the Pope, because if there's 2 people in there, that really means that there's 1 person. And so since you and the Pope are in the room, you must be the Pope. So trying to base science off of something that's obviously contradictory, this doesn't work. But basing something that we might have like 30 years of evidence for, or that we might, believe because it must limit to this, even if we don't have the formal mathematical argument. These are all things that are very important to investigate to make sure that we understand how to use quantum computers in the best way.
So in your view, what are the biggest scientific or technological hurdles slowing the transition from theoretical quantum computing to practical, widely used systems?
Yeah, good question. I mean, yeah, this is sort of a preoccupation with the field right now. One is that long term, we don't know how to make the quantum computer noise free. Whatever computer you're using on a daily basis or cell phone, a lot of years of development of quantum error correction, of classical error correction. Classical error correction has happened so that you can make sure that, like, if you had one of like the original cell phones, you'd have like your voice would sometimes like echo, like right in the middle of the conversation. I remember people being like, "Oh, you physicists, you should just." Yeah, right. You physicists, you should just figure out how to make a better cell phone. But it turns out that was like a big engineering question for a long time in electrical engineering. It was like, how do we get basically a better protocol to make sure that we actually receive the message that was sent? And so this took a long time, and you probably saw through successive generations of cell phones that things got better. One of the big things that we have to do in quantum computing right now is we have to do exactly that. We have to build in ways to make sure that the natural quantum fluctuations on the quantum computer are not there when we actually use it to get some useful quantity out of it at the end. So this is kind of a major technological hurdle that I think is on the roadmaps of most major quantum computer companies. But I would say that it's not the farthest thing away, because we've already had some rudimentary demonstrations of the most well-known versions of quantum error correction, things like a toric code, which is very complicated. But other things like, finding the point at which they can reasonably sustain a noiseless state on the quantum computer, some logical qubit that can be expressed there. These things, I think they're forecast to come by 2029. So maybe that's not so far away anymore. And I've been kind of interested in the progress in this and how fast it's come on. It used to be that we would say that those things would come in 50 years or something. Now it seems like it's around the corner. They're also branching out into 2-dimensional architectures, which would really help with this. And I assume that 3-dimensional systems, networks of qubits that are in 3 dimensions would be right around the corner. But I would say that, even with all this technological advancement and the Nobel Prizes that are coming for the coherent control of quantum states and for all of that, we still need good methods that are reliable on the quantum computer and good compilation and transpilation so that we can actually make those algorithms something that you can actually run on the quantum computer. And these, I would say, are some of the big challenges that we're looking at and that the community is looking at as well.
No, I think that's a good point. Because where we are with quantum computers is probably where we were in maybe the 50s or 60s, right? Because when I was in school for computer science, error correction was taught, but even one of the professors I had was like, you're probably never really going to encounter this because this is an almost solved. He's like, it's an almost solved problem. And we have this debate in the last couple of years was, do we keep this in the curriculum? Because, does it really matter? I don't know. Like, it became like a thing. And error correction is something I think everyone within the sound of my voice can understand, right? Because like one of the things, so one of my first jobs out of college was like my second or third job. I was working at barnesandnoble.com before they were barnesandnoble.com. And one of the store systems, if you look at any barcode,
Yeah.
The last digit there is actually an error correcting code. So like it doesn't have to be complicated. But it is something that is in everyday life, and it's largely a solved problem, at least in conventional or classical computers.
Yeah.
It's just fascinating. Like, kids today who go through, a traditional comp sci program, they're probably like, what do you mean error correction? I had a younger colleague ask me about why do you need to do error correction? And I was like, well, truth is, error correction has been a thing. It's just been solved. Although interestingly, for space systems, again, you're the physicist, so tell me if I'm wrong. For space systems, because cosmic rays or there's some kind of radiation that will occasionally mess with electronic systems, space systems have to have like a triple redundancy. So that way they check the math just in case, right? So the chances of one of them being impacted is very real, but the chances of all three of them being, or two of the three being impacted the same way isn't, not going to happen realistically.
That's exactly right. Yeah, there's a book on my shelf about basics of information theory, and it starts off with this guy Claude Shannon that was right after World War II, and he said, what's like the best way to make sure that the message that you send is received by the receiver? And so the start of this is always just that you write down 3 or 4 axioms, things that you assume to be true. It's like finding someone in New York is harder than finding someone in a small village, or that the probability of error should be continuous, or the other one that it should add like a logarithm, which is something you can derive. But basically, there's a theorem that comes out of this analysis by Claude Shannon, which is exactly what you're talking about, where they say that if you send the message multiple times, then you can take a majority vote of the answers and assume that that is the one that was actually meant to be sent. And if you do this slow enough and with some other caveats, then you can come to a conclusion that, yes, I did receive the right message and everything is as it should be. I think when you held up the barcode, I think that's the Reed-Solomon code that is there.
Sounds familiar,
I think that's the right one.
Because
I would say that go ahead.
No, my first job there was making basically tying into barcode scanners, and there was a whole book about this history of the barcode and like the technical specifications, how much of the barcode can be missing before it will just give up, and there's a whole science to it, and it's like everyday tech we don't think about. I'm sorry I cut you off, but
no, and that's actually a perfect example. I had a much more complicated example in mind. This idea that if you miss some of the information, you can still recover the message. In other words, extrapolate to the code word. That's exactly this idea behind information theory. So it's all coming out of this, and whether you use a Reed-Solomon code or a Polar code or something, these are all the same ideas that we want to implement on the quantum computer. I would say, to your point about the computer scientists and whether like error correction is actually something to study, like one, you're absolutely right. Quantum computing is very much a 50s, 60s thing right now. Even like the algorithms that we compare in quantum chemistry, they're best thought of in comparison with algorithms from the 50s or the 60s. So not like, you're not going to use these to make your cell phone. You're going to get very rough results. But then the other point that you're making about like computer science students, like, I mean, for both this field and artificial intelligence, there's a lot more to prove. And what I hear from sort of the modern computer science students is like, oh, whoa, should we actually get into this? So it's important to make advances in these fields.
But there's opportunity in those advances. Like, this is brand new, untouched land, so to speak. I mean, I was joking with a previous show, like they're still naming algorithms after people. Right. Like, exactly. And that's a good indicator that this is new territory, right? Like, so it's I mean, it's not going to be a well-worn path, but that's where the opportunity always is, right? Eventually those streets will be named after the first people who kind of, walk through those woods, so to speak, right?
Yeah, exactly. But it's scary, so it's like it's not.
It is very scary. Like it's not for the timid, but it's
like that's the fundamental training that you get in physics. Is it's like somebody goes to a physicist to hire them when they want to solve something that they don't know how to solve, And then
Right.
they assume that the physicist has all this knowledge that is there, but really you're just trying to put things together based on what you know. And yeah, it's exactly this process of being creative is scary.
Right. Well, it's always that tension between, physics and kind of engineering, right? Like physics is about the fundamental, understanding the fundamental laws, but engineering is, what trade-offs do you make to comply with the laws of physics as well as comply with whatever it is you're trying to do, right? There's always engineering is a science of trade-offs, so to speak.
But I think to your point, like it's very difficult to draw the line for some fields at this point. And this is a constant conversation that happens inside of physics departments everywhere. It's like, is this field at the point where it's more applied, and so like a chemistry department should be hiring these people, or is it so mathematical that a math department should have these professors, or should an engineering department be optimizing the photonics or circuitry that is required there? This is a really tough place to find this line, and I think it's even more difficult because for quantum information and quantum algorithms in particular, if you come up with an algorithm that is complete in a computer science sense, and what I mean by complete is if it solves one kind of problem, it solves every other problem in that class of problems, then it's like I show one algorithm to my students, but I might be sending them off into biophysics, and then maybe the next project is going to be on, I don't know, a quantum internet, or the next problem is going to be on like optimizing like train schedules in the UK. So from one algorithm in this field, you are going to intersect with a lot of theory that is going to come out of this. And I think that's the real, like, the challenge of being so interdisciplinary.
I wonder
kind of like how computers used by everybody. But,
yeah, that's what I'm going to say. Like, I wonder, like, how, what were these conversations had in the 50s, where you had the physics department, you had the mathematicians, you probably had electrical engineers in the room, all debating about like who should own what, right? Or like, and then, eventually kind of spun out to its own thing. I wonder if we're going to, kind of have a very similar conversations now and over easily the next 5 years, right? Like, I don't know.
Probably the equivalent conversation right now is what qubit platform is going to win out in over what time scale. To take your example from the 50s, like, so in the 50s, I think the Nobel Prize went to, it was definitely Bardeen and two other people for the transistor, inventing the transistor, which it actually turned out that a Canadian person had the patent for Shockley, I think, had the patent for this.
Oh, really?
Earlier, but then they took the idea from this and ginned it up, and then they won the Nobel Prize at Bell Labs. So before that, I suppose you would have had maybe vacuum tubes or something. I don't know what was in those original computers. But I'm sure that there were people that were like, no. You don't want to trust the solid state transistor. You want to go with the vacuum tubes. I know that there were people that were saying, well, the computers are just going to get bigger and bigger and bigger. But then it turns out that everything, the right technology won out through the scientific conversation. I would say right now, our big questions that we have to sort out is, what qubit platform is actually the best one to use? And I would say that the other one is, how do we actually use the quantum computer so that it's not just for defense purposes or for, whatever else we need it to be for. These are all the things that I think are probably the modern iterations of those age-old arguments that are still going to happen. Nothing ever gets solved. You just find new things to argue about.
You find new things to argue about. That is very true. No, I think it's there was also a science fiction movie I read, not a science fiction movie I read, science fiction book I read where there was about a society who built computers, but out of basically pipes and valves. So it was a fluidic based computer, and part of the plot was just how massive the thing was and how many people they needed to like pull the levers to do the computation and things like that. So like, but to your point, like obviously a transistor, vacuum tubes are more efficient than that, and transistors are more efficient than that. But to your point, like, do you really think we're going to settle on one type of qubit? Because that's one of the debates that we've had is like, I think it'll be kind of like fuel sources for vehicles, right? You'll have electric, you'll have, diesel, you'll have gasoline, and there'll be some, I think that we'll end up having the majority will be one, and then there'll still be like sizable minorities of other ones, kind of like we have with fuel, right? Like with automobiles. So most of it is gasoline, with an increasing EV, but also diesel also plays a pretty big role too. Like,
yeah, and continuing your analogy, there's also been proposals for organic qubits. So this
really,
there is also this like, oh, what's the sustainability angle, and how do we just take a
interesting.
regular chemistry system and tune the energy level so that we can manipulate the qubit states in that. So yeah, no, this is well taken. I think it's too early to say, like, as I was about to say, like, oh, well, single qubit readout is hard on this one, so maybe it's this one. I think it's too
Right.
early to say if there's some like breakthrough on one of these that maybe that'll work out. I will say that I've been really impressed by photonics and spin qubits. I think that the ideas behind that are really interesting, and it is kind of a, like, if I was going to teach a course on it, I'd probably start with a photonics-based setup, just because it's like, you talk about Alice and Bob, you talk about qubits
Right.
being, states being entangled with each other, and it's just a very obvious manifestation of all of those things. But the leaders right now, I would say, are still pretty much superconducting qubits, just because
Right.
they have, it's scalable. You need to keep it at low temperature, but it allows you to have a nonlinear response that is still stable. And so this is kind of the, I think, the direction that people are going in right now, at least.
Yeah, I think photonics is probably going to win out. It'll be the gasoline, so to speak, of the future. Just because the room temperature thing, I think, goes a long way.
Yeah.
To making it practical, right? You can scale, super cooled systems, but the cost of that's going to be astronomical.
Oh yeah. That's
especially
true.
especially as we think about sustainability and whatnot. I live just across the river from Loudoun County, Virginia, which is apparently, somebody told me this, it's Data Center Alley they call it, but apparently Loudoun County, Virginia has more data centers than China, like the entire country. And
That's crazy.
if you, I don't know if that's true, but driving around there, you could believe it. Like, it is literally, I can't tell you, we were in the middle of shopping for a car, and we were at a big car dealership there, and like, every building was an office building without windows. Like, they were clearly painted to look like an office building. But one of the big complaints is the energy usage and the noise and things like that. So I can't imagine, those are just cooled to, room temperature. I can't imagine if you have to get them down to like, what, 1 or 2 Kelvin, right? Like, how much more pollution and how much noise,
It's amazing that we even have that much data in the first place. Like, if I think about how much data, I've never seen like average amounts of data that people have, but it's like, my total data footprint must be less than 100 gigabytes, maybe with some videos or something floating around. I'm sure that this is, making a balloon or something, but, having only a couple of gigabytes per person, it's like, wow, okay, so there's like a lot of people using this, plus there's probably like medical data that's saved, or
right,
like
or your
photos that are sitting
browser
around.
tracking data, your mouse data. Like, there's a whole lot more data.
Yeah.
There's data you know about. It's probably like an iceberg, right? There's what you know about and then there's what was really there, right? From government records to all that sort of thing. Yeah.
Yeah. But we're
So-
sort of waiting to see how much better quantum computers can be, because whatever that number is, take a logarithm of it, and that is how many qubits you need to represent that. And it, like, it's sort of an order of magnitude game that you're playing. So if it's a gigabyte, then it's, I don't know, a few dozens of qubits in order to represent all of that. So even if you need to cool the quantum computer down, there's still the opportunity
you would
to
still
have it,
get
run
you
on
would still
tiny
get a
chip.
saving. That is a good point. I hadn't thought of that. And you mentioned logarithm a few times, and it's been way too long. My teenager's taking AP Math.
Sure.
And I don't need to give him another reason to, think his old man doesn't know anything. But and I also forgot. So logarithm is a way to break down a number into a smaller number.
That's
is that okay?
So without busting out a slide rule, which
right
they don't use anymore. So if you're picturing the number in like scientific notation, or if you're just picturing any number to the power of some other number, the magical property of the logarithm is that whatever was not the exponent stay, like the logarithm is going to produce some other number. The key point though is that the exponent that comes down in front. And so when I say like, if I say like a million, think like 10 to the 6. If I
Right.
take a logarithm of that base 10, then I get 6. So
Oh, okay. So
this
2 to the
whole
power
idea,
of
like
32, you would get 6.
yeah,
32.
yeah.
32. Sorry.
Yeah, base 2. Yeah. So logarithm base 2 on 32 would be
Gotcha.
6. Yeah, so the base of the logarithm matters. You're thinking qubits, which is the right one for this podcast. I'm
Okay,
thinking
okay.
like 10 level qubits.
I get you. Okay. No, that helps. And the last time I had to deal with logarithms on a day-to-day basis, I think Kurt Cobain was still alive. So it's been a while.
Smells like mathematical rigor.
There you go. There's the title for the episode.
Okay, well, yeah.
So,
But-
the more we talk about this, quantum technology is notoriously hard to communicate. What strategies do you use when teaching and explaining these concepts to students and to non-experts?
Well, you've seen a couple of my pitches. The first thing that I'll say about quantum information, and one of the reasons that I like it, it does not have a good PR department. I think we can just admit that, right? Like astrophysics, they can show you a video of like 2 stars colliding. Ooh, or like the amazing images that come out of the James Webb Telescope. These are like
Right.
these are fun to look at. If I'm giving a talk, it's like, here's a very abstract thing that I'm going to talk very abstractly about. And then if I'm successful, you're going to take it for granted, just like you take your wall clock for granted after it's been engineered, just like you take your computer for granted after it's been well engineered. You're not constantly thinking about like what's going on underneath. So getting people to engage with the minutia of this is very, very difficult. And I think pretty much everybody in this field has an experience where you've been put up for a 3-minute thesis or some sort of short public talk about it. Oh, very hard. If you can't educate your audience over an appreciable amount of time, you're relying on their prior knowledge, and this is way off the deep end. So it sort of depends on what I'm talking about when I give a talk. You sort of saw my pitches already in our conversation, because when I was talking about error correction, I went back to classical error correction. And so a lot of students have come to me and said, can I please learn more about quantum error correction? And I say,
Right.
Sure, let's go study classical error correction, because all the ideas poured over. And I try and reason by analogy between
Right.
the two. And then the other, like if somebody comes to me and says like a quantum algorithm, I'm just like, okay, let's do a very simple example and work through something in a paper in order to do this. But yeah, I mean, it very much depends on your audience, depends on what their background knowledge is, depends on what they want to use it for. Like politicians, you're going to gear more towards like your encryption might be broken by a quantum computer. Right. If it's somebody working in medicine, we might be able to model a better molecule. And you basically reason from what they know to, and then somewhere in there, I'll say, okay, this is the magic that I have. This is the thing that I think I can do that you think maybe is impossible or haven't thought about doing before. But this is the part where I think the quantum computer can sit, and let me go try to solve that for you, and we'll see how it goes.
Okay.
Very cool.
So what are the essential skills or mindset you think new students should develop to contribute meaningfully to quantum information science?
That is such a deadly good question. That's so good. Yeah, I mean, the actual skill set that you would need in order to be successful in this area, I'd say one is like a flexible thinking. There are deep divisions in physics that exist. There's preferences. There's even entire articles that have been written in like a monthly column format, bashing other areas of physics over the 20th century. Like, let's not use computers. Let's reason everything out with mathematics.
Right.
And I think having students that come in fresh is such a valuable asset to this field, because sometimes they see things through a completely different lens, or they pick up a little computational skill that is going to help you. Like, I worked with 3 really good undergraduates last summer, and I had a project that I thought was going to take a graduate student. But those 3 guys, they just worked together, asking my other excellent graduate student some questions, and she was able to answer. But they were able to essentially put everything together just because they didn't have any preconceptions. They were even solving things that we had an external colleague, and he did, he's already been thinking about it for a little while, so he went down the practiced way. But they just went in a particularly new direction. I would say that I'm a little bit partial to physicists and people who have a physics background. No offense to everyone else. Like, I definitely need chemists in my group because they know about things that I don't, like electronic structure. I need engineers to talk to because they know about how to actually put these things into experiment and what I should expect if I actually make a claim that this will be implementable on a quantum computer. I definitely need mathematicians and computer scientists for the rigor of what happens. But in terms of coming from a physics background and trying to innovate and trying to be creative in the field, I would say that if you just have some math background and if you're willing to touch a computer and to program a little bit, I think if you just come in relaxed and creative, I think this is the best set of skills for anybody coming in the academic environment, I should say.
Yeah, and I think that's an interesting segue into, this is a field where it is going to be commercialized over the next 3 to 5 years, if not already.
Oh yeah.
I mean, it's definitely like what I definitely think that there are different cultures amongst academia and kind of the commercial startup crowd, which is probably an understatement. But how do you see that being mitigated, like in terms of conflict?
Yeah, somebody was telling me about condensed matter physics, and they had seen it kind of rise, and then they decided to switch to quantum information. And I'm not sure that this quote is quite accurate to condensed matter physics, but I like the quote, so I'm going to preserve it here. Everybody was really collaborative when they were successful, and then as things sort of got, more static and things were less successful, people started to not be so collaborative.
I see.
So I think it's a little bit of luck, and I think it's a little bit of, we need to stop trying to put our names on things, and it's very important to actually get the thing solved.
Right.
Like, I would say that AI has this problem quite a bit right now. AI, it gets things wrong. There haven't been an explosion of materials come out of this. That could be that we're going to find ways to do it in the future.
Right.
But this additional pressure that modern science has of the companies need to make their quarterly profits and they need to do fundraising. This is something that is very, very new in the grand context of science and publicly funded science in particular. So I think it's very important that, like, if you're a student or a postdoctoral researcher or a new faculty or something, very important to just kind of play your game and see how things are going to turn out. And even if an idea is not popular now, maybe it will be soon.
Right.
So what signals should industry and policymakers look for to know when quantum is moving from experimental to operational?
Sure. Yeah. For policymakers, this is I think it's a question of what your motivations are. I was really lucky, and there's a program called Science Meets Parliament that is up here in Canada. And so I as one of the research chairs, I was allowed to go to the Houses of Parliament. It was a really great experience. But one of the things that we were talking about in the lead up to this was how you would message for what I know, because I'm from the US, and how you would talk to a US politician versus a Canadian politician. I think sort of the consensus is that US politicians have a long history of looking at their constituencies and identifying how technologies have brought jobs and brought economic development and how they've helped things. In Canada, we're a little bit newer to that idea, and there's been some recent headlines about this in the newspapers about why it's important to fund quantum computing and quantum mechanics. So if I was talking to a politician about this, I think I'd probably start off with like what is your motivation? Like, do you want to just engineer on what there already is? If so, that will change how you fund things. If you actually want to innovate and you actually want to push technology to the limit, history has shown us that funding in science has been so lucrative it has a huge return on investment. This is why a lot of immigration programs are set up to bring in high knowledge people into a country, is because it just has huge benefits. I think kind of what I've been seeing with the recent activities and things is that idea of innovation from the end of World War II in particular, of publicly funded science. I think people are have sort of lost the image of like what science can provide. Like huge technological changes come from this stuff. But we're at a point now where we're promising it's going to happen in a couple of years, which is the standard scientific pitch. But then if we don't deliver on it, I think people just get an idea into their head that maybe it's not coming, maybe the money isn't worth it, but it always is. It always leads to good things. And there's been a huge raft of funding that's come out in Canada that I'm very grateful for, and that they seem to be very serious about funding this area. And I think places that invested in are gonna reap the benefits as they go forward.
Yeah, I mean, the next wave of economic innovation is always in some weird corner of science that hasn't been explored yet, right?
Yeah.
I mean, you know, Claude Shannon, when he was working through his stuff, was even when you go back to Babbage and Ada Lovelace, right? Like that was just some weird science project that, you know, no one else was interested in. Ada Lovelace saw the potential, but no one else did, right? It wasn't until World War II where, hey, we need to crack these codes.
Or we need to figure out what those physicists are doing because they just built a bomb that can level
yes,
cities.
Exactly.
Like, we better keep track of these guys. Like
right.
But you know, social scientists have figured out that traditionally the best way to do it is to give a lot of people at least a little bit of funding and let the winners happen naturally.
Right.
Definitely you're using good examples there of historical situations.
Sorry, Candace, I cut you off.
No. I'm just thinking. It kind of taking in everything. So let me ask you this: what role do open source tools and academic collaboration play in accelerating the progress compared to proprietary or closed approaches?
This is such a weird time for open source software. It's been amazing, even just over my comparatively short scientific career. It used to be like everything open source is good. And I still encourage my students to use a lot of open source software and things. Weirdly, I've been hearing, even just with this disruption from AI, that some computer science professors are saying, don't put everything online because it just gets scraped by a large language model. And then I haven't heard the full argument about that. I just heard sort of the top thesis statement. Even little things like a driver to interface with general printers. Like I think some big company bought up the driver that a lot of computers use to interface with printers. And the transition away from like open source standards with GPUs towards the more proprietary versions of those software. It's like there, even just in my limited scientific career, there's been a transition towards closed source technologies. I don't know what's going to win out. That's kind of a major question for me right now in my research, and what'll be doing. And as we deal more and more with research security, it's like we have to play these games of making sure that our computers are secure and that they don't cross certain borders and things like this. But I would say that the battle between open source and closed source, if you're making your own stuff, I think you have to go with open source. So most of the people in my group will use a Unix-based operating system rather than something that is more proprietary, something more general. And it's really, really important that if you're making your own, like if you're making innovations on computer stuff, you better write your own code. Trying to rely on somebody else's code to be super general enough to make new discoveries, this can be difficult. So I don't have a perfect answer for this. It's just for research, open source is still good.
Yeah, well, it's the cost of admission is low too, right? Like that's
yeah.
And I saw on your profile you linked to, and this is going to get a little nerdy, Candace, so I apologize in advance. Saw you have at least 2 projects on GitHub.
Yes, at least 2.
And they're both in Julia. And I find that interesting because Julia was supposed to be this, I started in AI way before it was cool. So there was Python and R, but Julia was meant to be like a third contender. Now, what I've seen in industry is R is still used by companies. Python is definitely the winner. You don't hear much about Julia. So that, you're probably the first like Julia programmer I've ever had on a podcast. So I have to ask, like, where is it used? I don't mean that. I don't want to sound like a smug Python coder, right? Because I have no right to be a smug, because I used to write Silverlight code and Windows Phone apps, right? So like smugness is not something. I've learned my lesson about being smug. No, I'm just curious, like, because like, and for people that want to knock on Julia as a language, Jupyter notebooks, the J part is Julia. So sorry, go ahead. Like,
no. So that was the reason that I've been coding in Julia at this point. The reason that I maintain those within the group is pure pragmatic reasons. Students coming into my group from a physics background don't necessarily have all the high-level coding skills that they would need in order to quickly sort through a C++ or a Fortran code or something lower level. Even something like Rust, I would say, would be just a little bit more than they would get. So given a master's student who has nominally 2 years to complete their degree, and they take courses for maybe the first year, and then they get a summer, the fall, and then they need to start writing up their thesis, I have to find ways to lower the amount of time for people to get into the research. Now, the question is, could I have accomplished the same thing with Python? The answer is yes, except that there's this statement that floats around Julia that is very contentious, that Julia's for loops are optimized in a way that you can get performances like lower level languages. So the original reason that I started in Julia was I wanted to figure this out. It turns out that it's a more complicated process than the help pages would have you think. But those codes they do run at the lower level language standard for speed. In some cases, they're a little bit faster. And I've actually, I think that one repository is starred 50 times, whatever that means. But I've noticed that some of the tricks have been filtering into other codes. Maybe people are finding them independently. So very much like a developer's code that is listed there, but purely for pragmatic reasons. If I had to go back and start it again, if I would have switched to something like Rust, I would have lost the ability to do multiple dispatch in Julia. The idea that you can have one function that takes many inputs. You don't have to explicitly make all the functions in Julia. And this makes programming much easier. But there are, there's trade-offs. There's things about it that I'm like, why did I even touch a computer in the first place? Why didn't I just stick with theory? But at this point, it's just a pragmatic reason so that the students find it a little bit easier. And I won't comment on the name of the language. It probably could have had a different name, but it's okay.
No, I was just curious, because it was one of those things where it was going to be the next big thing, and it definitely has traction, but it never really, I think, lived up to its potential in terms of what it can do.
A lot of people filtered in, made packages, and they're deprecated now. So the importing of, I think, PyPlot into Julia is not working, and the PyPlot, I think, still looks better than the regular Julia standard.
Right.
So I do think they do suffer from a lot of deprecation and things, but I would say scientific software. Maybe to your point, there's a network of supercomputers in Canada. Turns out we're one of the only groups that uses Julia. But our new computers that are coming in, it's like these are going to network really well with Julia. And I don't know. It's for ease of use at this point because so much work has gone into it already.
All right, that makes sense. Again, then I don't have a favorite language anymore, right? I think Python. I learned the hard way. I used to be a C# developer, right? Like before that, I was
no.
Before that, I was
sorry.
Before that, I was Java, right? Like it really had more to do with commercial availability of work. Really was and like now I go with Python. Python's not the best language I've ever worked with, and it's certainly not the worst, right? Like it's it gets the job done, right?
Yeah.
And it can get a lot of different jobs done.
Yeah, like Julia's Python, but you don't have to worry about the indents, and you can optimize the for loops allegedly.
Yeah.
And I don't find too much difference. I think honestly, if there's like a student out there like listening to this and it's like, oh, what do I do? Just learn any computer programming language.
Right.
The skills and the tools that you'll pick up learning just one, they'll translate to other languages. And if you start at Julia and you don't like explicitly set types for variables, you'll pick it up through time when you move to the other thing. And
Yeah, the
if you get into more advanced,
compiler will tell you. Like,
yes, exactly. Yeah,
the compilers aren't shy. Well,
No,
and like I started with BASIC on the Commodore 64, right? Like,
I did too, but
awesome.
Yeah, BASIC was the first one I touched. Yeah.
So BASIC is, and then there were that was arguably whether or not it's compiled, and I think it depends on which implementation, BASIC and all that. But I mean, like, again, you're right. It's the thinking in structures, thinking in process, thinking that that's the skill. The how you do that is secondary, and
Yeah, exactly. So, but I think as we sort of transition more to like TikTok and stuff, where you don't have to punch things into a keyboard, very important that we maintain those coding skills. Like,
absolutely.
Maybe I'm fighting uphill because it's like arguing that someone should continue to learn like car mechanics, even as we transition to like, cars being more computerized. But I still think that like knowing how to type quickly, maybe that's a good answer to Candace's question. Like, if you know how to type quickly, that can just pole vault you over people who might be smarter than you, like, but can't type as fast. So, I mean, little soft skills like this, like computer programming, like, I don't know, what's another good one? A little bit of public speaking, a little bit. Oh yeah,
public speaking will put you the top 10%.
Yeah.
Even if you're not good at it, even if you're okay with it and you're comfortable with it, you're in the top 25% right there. Because most people will say, like, what's this? There's some ridiculous statistic where, like, people are less afraid of jumping out of a plane and speaking of something like that. But like, I don't know if that's true, but just even if that sounds plausible is the problem, right?
Yeah. No, I think all these points are well taken. But like, how to recommend success? At the end of the day, you kind of have to be lucky. Like, you can have all the skills in the world, and just you went left instead of right, and so you do need a bit of luck at some point. But you can also kind of make your own luck. So I don't know.
Make your own luck. I like that. So
yeah.
So that was fantastic. Fantastic.
No, that was really great.
Thank you.
Thanks for coming on the show. I really enjoyed it. And any final thoughts, Candace?
Honestly, there's so much more to talk about, but I really enjoyed it. I want to work on those soft skills that are needed for better PR and better communications and better marketing. That's it. Yeah, that's where I am.
Awesome. And where can folks find out more about you, Thomas?
What you're up to? I've got a research website. If you go to the Department of Physics and Astronomy or the Department of Chemistry websites, it links to my own website. We've got some really exciting work that's coming out of the group on quantum algorithms and classical algorithms and things with quantum computers. And feel free to reach out on my email on those pages as you like.
Awesome. With that, we'll play the outro music.
Breaking the mold, science and sky beats, it's bold and it's gold. The multiverse is skanking in time. Black holes are wailing in a horn line so fine. From Planck scales to planets, they're connecting the dots. Candace and Frank, they're the cosmic hotshot. Breaking the mold, science and sky beats, it's bold and it's gold.